Inverter Advanced Course Specifications and Precise Performance Matching Logic. Hello everyone, welcome back to our class. Today we are going to have an advanced course of last month's fundamental class. I believe you've already built a solid foundation in power forms and product classifications. Today, we will focus on some other industry abbreviations and work through the advanced knowledge. The 9 core abbreviations we are studying are the real hard currency about inverter design, selection, and application. They are all universal industry standards. No matter which type of inverter products you work with, this material will be directly useful. Part 1. Detailed explanations of core abbreviations. Let's start with our core content. The first section is a detailed breakdown of key abbreviations. We will cover 9 core abbreviations spanning 6 dimensions: energy storage systems, electrical parameters, hardware components, industry standards, international certifications, and application forms. These are not just the foundation of advanced learning, but also are the core basis for product design, compliance, and performance matching. Once you clearly understand this knowledge, the following everything will go smoothly. The first one is ESS, Energy Storage System. Simply put, it's a power dispatching framework built around the inverter. Think of the inverter as the heart of this system. It integrates the battery, BMS, photovoltaic modules, and monitoring systems. The inverter's primary job is bidirectional conversion of DC to AC and AC to DC. Through this, the system can store energy, release it, and perform intelligent dispatching. So, what does an ESS actually do? Its core value lies in 3 things: smoothing peak valley differences in grid, ensuring reliable power supply, and improving the absorption rate of photovoltaic energy. And depending on the application, ESS falls into 3 categories: residential ESS, commercial and industrial ESS, and grid-scale ESS. The requirements of these different scenarios on the inverter vary significantly, such as power rating, response speed, and compatibility with multiple devices. The second abbreviation is FCC, Federal Communications Commission. This one must be kept firmly in mind. If you want to sell inverters in the North American market, FCC certification cannot be ignored. It's a U.S. federal regulatory body, and its certification standards are legally required. Its core focus is managing electromagnetic interference and electromagnetic susceptibility during inverter operation in order to ensure that the electromagnetic signals generated by our devices don't interfere with the grid, communication equipment, or other electrical products. The specific certification required is FCC Part 15, which covers electromagnetic compatibility for civilian digital devices. Once your product passes, it must bear the compliance marking on its nameplate. Without this certification, you cannot sell or use your product in North America. It is one of the essential entry tickets to the North American market. The third one is PCB, Printed Circuit Board. Every core electronic component in the inverter, like power devices, control chips, sensors, capacitors, and resistors, is on the PCB, which provides all the electrical interconnections. It is the absolute core of hardware design. The PCB's layout and routing directly determine the quality of the inverter across multiple dimensions: electromagnetic compatibility, thermal management, operational stability, and service life. For example, the power circuit PCB must use wide copper traces to ensure adequate current carrying capacity. The control circuit must be physically isolated from the power circuit to prevent signal interference. For high-frequency and high-power inverters, the demands on PCB substrate material and impedance matching are even stricter. There's no room for compromise. The fourth is EMC, electromagnetic compatibility. It is a core electrical performance indicator for inverters. In simple terms, EMC means that while the inverter is operating, it must not generate electromagnetic interference beyond the allowed minute. At the same time, it must be able to withstand interference from the complex electromagnetic environment around it and continue to function normally. EMC covers two dimensions: EMI, electromagnetic interference. The electromagnetic signals a device radiates or conducts outwards, and EMS, electromagnetic susceptibility, the device's ability to receive external interference. The inverters must pass the EMC certification standards in each target country or region. For example, FCC in the US and CE in Europe. If they don't, at best the device malfunctions or interferes with neighboring equipment. At worst, the products cannot legally enter the market and loses its commercial viability entirely. The fifth is IEEE, the Institute of Electrical and Electronics Engineers. It is the world's most authoritative professional organization in the electrical and electronics fields, and it is also the body that formulates the universal technical specification for the inverter industry. Inverter designs, grid connection, testing, and field deployment must all strictly follow IEEE standards. Adherence to IEEE standards is the core technical foundation for a product to achieve standardization and earn recognition in international markets. The sixth is UL, Underwriters Laboratories. Worked with FCC, UL is the other essential core safety certification ticket for entering the North American market. It's an important global reference for inverter safety design. The key standard here is UL 1741, which is the dedicated safe standard for PV and energy storage inverters. UL certification covers almost everything: electrical safety, mechanical safety, fire resistance, and environmental safety. It examines every detail from component selection and circuit design to protection, structures, and fault protection logic. The seventh is ISC, Short Circuit Current. This is a core electrical parameter for matching photovoltaic modules with inverters, and it's something you absolutely need to calculate accurately if you work in selection or system design. It refers to the maximum output current of a PV module when its output terminals are short-circuited under standard test conditions. Here's a critical point. The inverter's PV input side must be capable of withstanding the ISC of the PV modules. The rated current of protection devices like fuses and circuit breakers must be precisely matched to the ISC. When designing PV strings, the total ISC cannot exceed the inverter's maximum circuit input current. The eighth is UPS, uninterruptible power supply. An UPS is an emergency power supply device with the inverters as its core component. When mains power is suddenly interrupted, it switches to battery power within milliseconds, ensuring crucial operation without disruption. How fast is the transfer time? How precise is the voltage regulation? Can it handle overloads? How good is its anti-interference capability? All of these are the key benchmarks for evaluating a UPS performing rating. The final one is VOC, open circuit voltage. This is the critical voltage parameter for matching PV modules with inverters. VOC refers to the terminal voltage of a PV module when its output terminals are open-circuited under standard test conditions, STC. There is an important characteristic. In low-temperature environments, VOC rises noticeably. For every 1 centigrade drops in temperature, VOC increases by approximately 0.3 to 0.5%. This is a detail that absolutely cannot be overlooked when designing systems in areas with very cold winters. The inverter's maximum PV input voltage must be greater than the maximum open circuit voltage of the PV string at the lowest ambient temperature at the installation site.